All right, everyone. Can you hear me all right? I'm hoping so. Maybe. Yes? Yes? Okay, perfect, perfect. Can you all see the screen as well? I'm at the midterm. I just want to make sure that you all can see the midterm as well. Wonderful. Thank you, Jamal. All right, who's ready for some fun? Kevin, you in the chat? You ready for your fun? I know Kevin's in here. So just like in person, I'm going to pick on him online too. Yeah, there we go, Kevin. Perfect. All right, so we're going to go through the exam together. As we're going to see, it's not very challenging. A lot of the midterm one, the first midterm exam, has to mainly do with just remembering specific properties of tensors as well as basic linear algebra operations. If you're familiar with both, the exam is going to be pretty easy. This is going to be the 2015 midterm. So this is the 2015 midterm. 2014 is already posted, and I'll probably do 2016 next year. So you're all welcome to join the review session next year for 2016. Chances are you probably won't want to, though. All right, so this is going to be 2015. And as I was saying, if you remember the properties, this should be a very nice, quick exam. And if you don't remember the properties, it's still going to not be too bad because you can just throw everything into Mathematica and do a trial and error sort of process to figure things out. I have found that if you remember the properties, this exam takes maybe 30 minutes to do. If you don't remember the properties, it might take an hour and 10 minutes. So either way, you should be in the clear with the time frame that you are given. So if you have any questions, I have the Zoom chat up. I don't have it on my iPad, but I have my computer screen. And my computer screen, which has everything on it, is being recorded. So the Zoom chat is being recorded so everyone can see the questions I'm referring to. In addition to what I'm actually writing, that will also be recorded. So I will post that after we're done our session today. I have it booked for 2 hours. I don't think it's going to take 2 hours. This is a pretty quick midterm exam. It's only 25 questions. And again, if we know the properties, a lot of them are pretty self-explanatory. All right, so let's begin. The first thing I want to do is, of course, you got to write your name. So given name, of course, Kevin. I didn't know his last name until he was just so kind to post it in the chat. So thank you so much, Kevin. And we will begin. A nice thing for you is you don't have to write your name. The exam is all through E-Class, so it'll be linked directly to your E-Class name. So you're good to go. All right. So if there's no questions, I'm just going to begin. If you do have a question, feel free to interrupt me at any time. Or if you want, just post it in the chat and we can go from there. All right, so the first question says, the following figure sketches the process of an orthogonal change of basis from the orthonormal basis set B to the new orthonormal basis set B prime. If the components of U in the basis set B are 1, 1, then the components of U, or U prime, in the basis set B prime are. And if we look here, it's a standard change of basis question. And we know that for change of basis, if I want to find my U prime, it's going to be equal to a transformation matrix Q multiplied by U. And if we look here, we already have what U is. The question gave it to us. It's 1, 1. So that one's not too bad. I don't know why it kind of lagged behind. Let's see if I can highlight it properly. Oh, I must have a little dead spot in my iPad or something. Interesting. Oh, yeah, see, I can't get that one spot. But basically, the only thing that we're missing is Q. Now, this is kind of a mean question because if you remember in the assignments, we would always base Q on the angle that we're rotating something. So typically in the assignments, I would give you, let's say, this value of theta right here, and then we would be able to calculate what exactly Q is. In this case, we're not given Q. And we're not given an angle, so it's very hard to determine Q. If you're ever given a question, and here's the big hint, and I'll highlight it in a different color. If you're ever given a question where it gives you the basis set and the new basis set, so all the values like this, this is a hint that what you need to do is you need to use the formula that Q is equal to EI prime dotted with EI. So this would be QIJ. So this is the formula you want to use. Again, if you're given both the basis set E and the new basis set E prime, you just want to go to this right here. So I'm just going to scroll back and we just say, okay, well, if I wanted Q11, for instance, it's going to be E1 prime dotted with E1. And I have E1, I have E1 prime, so all I would need to do is just do the dot product. So I'm going to erase the ones that I don't need right now. I'm focusing on the two that are highlighted. So we know it's going to be 0.8 multiplied by 1 plus negative 0.6 multiplied by 0. And of course we get that this is equal to 0.8. Now I can repeat this process for the other three remaining Q's. So Q12 is going to be E1 prime dotted with E2 now. And if we were to do the math on that, we find that this is equal to negative 0.6. If I wanted to do Q21, this is going to be E2 prime dotted with E1. And this, of course, is going to be equal to 0.6. It's very straightforward dot product. And if I want to do Q22, it's going to be E2 prime dotted with E2. And once I throw everything in, I get 0.8. So this is how we can find our components of Q. Now, there's a little trick to this question. I wanted to show you kind of the hard way in case you forget the tricks. Again, the whole midterm is based around these properties. If you forget the properties, it's okay because we can do it the long way that we just did. But if I were to write out Q right here, we are going to see that something special actually happens. So just filling in the blanks, we have 0.8, we have negative 0.6, we have 0.6, and we have 0.8. Now, the special thing that I'm referring to is if we look at what our Q is and compare it to our basis set, or specifically our new basis set, there's a lot of similarities. If we look at the first row of Q and we compare it to our new basis set for E1, they're the exact same. If I look at the second row of Q and compare it to our new basis set E prime 2, they're the exact same. So here's the trick. If your original basis set is 1, 0 and 0, 1, then what Q is going to be are just the rows of the new basis set. So my first row is just going to be E1 prime. Oops, switch from the highlighter. My first row is E1 prime, and my second row is E2 prime. So if you remember that trick, you can find Q rather quickly. But if you don't remember the trick, it's no problem at all, because right in the notes we have this nice formula and you can calculate everything out manually. So again, if you know the trick, it's quicker. If you don't know the trick, it's still perfectly fine. You can still figure it out. So I'm going to erase some of this highlighting because my screen is, oops, I'm erasing too much. My screen is starting to look ridiculous, because now that I know what Q is and I know what U is, if I were to actually do the multiplication, I find that U prime is going to be equal to 0.2 and 1.4. So that's just doing the multiplication because I know everything in the formula above. And if we were to compare this, we can see that this is answer A. So does that make sense to everybody? Any questions or concerns so far? All right, sounds good. So we will move on to the next one. The good news is this question was a bit of a longer one. So if this is considered long to you, don't worry. This is one of the longer questions. They get a lot quicker. Now this question's pretty fun. Question 2 says, let x and y be basically n-dimensional vectors, and let 0, or let a not equal 0 be a real number such that x is equal to ay. Then the projection of y onto x is equal to, And you're going to see a lot of these type of questions. And we just basically have to go to our formula for projections and manipulate it a bit. So we know that if we want the projection, and in this case it's y onto x, so x is at the bottom, y is over here, it's going to be y dot x divided by the norm of x squared multiplied by x. So this is the actual projection formula. This is in everybody's notes or your formula sheet if you chose to make one. This is basically given to us. And all we're going to do is substitute this property that x is equal to some scalar multiplied by y, where that scalar cannot be 0. So basically what happens when we substitute everything in, we now have y dotted with, oh, my pencil's not really working sometimes. It's very interesting. So y dot with alpha y. On the bottom we have the norm of alpha y squared, and then we multiply it by alpha y. Now what basically happens here is there's a lot of simplification that can be done because of the dot product. The first thing I'm going to do is I'm going to look at this term right here. If I want to, I can actually rewrite it as follows, where I'm going to take my alpha out and I can go y dot y. So that's all I did, was I took my alpha out. With the dot product you can do that, and I'm going to do the same thing at the bottom. So this little squiggle right here, this is actually equal to alpha y dotted with alpha y. And what I can do is I can take both alphas out to get alpha squared y dot y. Now at the very end here, we are just going to keep this alpha y the exact same. And the thing that we now have to remember, so I'm just going to erase this so I can keep going, is that alpha is just a scalar. So every time I have a scalar divided by a scalar, it's going to cancel. So this alpha combined with this alpha, they're going to cancel now with this right here. Another thing that we know is y dot y is also going to be a scalar. So this resultant y dot y is going to cancel with this one down here as well. So at the end of the day, I am just left with simply y. Now, none of my answers here really have just y except for a couple, so we can eliminate c and d because we know it's just y. It's not alpha y and it's not 1 over alpha y. If we look back to our relationship above, we know that y is actually equal to 1 over alpha times x. So if I were to look at my answers now, we can see that this is actually going to be answer number A. So does that make sense to everybody? Is there any confusion yet? I'm hoping it's going pretty well so far. These are kind of the harder questions, so if you can understand these, it should be good to go. All right, no questions. Again, just please interrupt me if there's any problems or concerns or anything like that. Okay, sounds good. So moving on to question number 3, it says the following set is linearly dependent set of vectors, or the following set is a linear dependent set. This is one of them that if you know the properties, it should be very, very simple. And the reason why is because we know that if anything ever contains the 0 vector, which we have right here, it's going to be linearly dependent. We know that immediately. So if I was to actually do this question and I see this, I can circle B right off the bat and there shouldn't be any problems or concerns, because if I ever have anything with a 0 vector, it's going to be linearly dependent. Now, let's say you forget that property and you're saying, okay, Clayton, well, how do I actually determine if something is linearly dependent? Well, again, all we are going to do is we're going to solve the following equation where we have some constant multiplied by our first vector. In this case, it's 1, 2, plus some other constant, so we'll say alpha 2, multiplied by our second vector, and it's going to be equal to 0. So if I forget that property, what I would have to do is I would have to solve this equation for every single one of these 3 choices. Now, if it's linearly dependent, what that means is alpha 1 or alpha 2 does not equal 0. So if I can ever find a case where one of those does not equal 0, it's going to be linearly dependent. If I were to look at my first part right here, my alpha 1 multiplied by here, well, the only way I'm going to get that equal to 0 is if alpha 1 is equal to 0. So far it would be considered linearly dependent, or independent, sorry. However, if I were to look at this part right here, this second part, we can see that alpha 2 can be absolutely anything, and it will still be equal to 0. Alpha 2 can be 1, it's going to be equal to 0. Alpha 2 can be 69, it's still going to be equal to 0. And since alpha 2 does not equal 0, we know that it's linearly dependent. But again, the trick is any set that contains the 0 vector will always be linearly dependent. So that's kind of the little trick for question number 3. Is there any questions so far about question number 3, or is everybody still pretty happy? All right, I'm going to assume everybody is still happy. Can someone just throw something in the chat to make sure that I'm actually online? I don't even know if my internet connection died and I'm just talking to myself. Oh, okay, perfect. So everyone's still here. Thank you so much. All right, so we're going to move on to question number 4. Now, this is a good question. If you came to the midterm review session, you're getting your money's worth, because I'm going to let everybody know that this is a very good question to know, especially for the midterm coming up. So it basically says, let A be a set where X is a 3-dimensional vector, and we have the restriction that the norm of X has to be less than or equal to 1. Okay, so we have a vector X that can be absolutely anything as long as its norm is less than or equal to 1. Now, it says this set basically represents what? And we have two different things that we have to consider. The first one is this going to be a ball, or is this going to be a cube? The second part is it just the surface, or does it contain the interior points? So that's the second distinction. One of them has the option that it's just a surface. One of them has the option that it's the surface and the interior points. Now, even though we have a 3-dimensional vector, as we can see, it says right here that it's in R3. We can kind of analyze this as a 2-dimensional vector to give us some basically insight into what we're looking at. So if I were to create a 2-dimensional plane right here, and I were to create a bunch of vectors that have my norm equal to 1, we know it's going to look something like this. This would have a norm of 1. This vector over here would have a norm of 1. And I can just kind of go around and draw a bunch of vectors with a norm of 1. And what will happen, as you will see if you were to do that, is that you actually get a very nice circle if you were to do this. And the radius of the circle is going to be 2. Because we know from right here, actually the radius is equal to 1, the diameter is equal to 2, but we know that the length of each one of these vectors has to be equal to 1. So from here we can actually conclude that this is going to be in fact a ball. So I can eliminate any option that says cube. We know it's going to be equal to a ball. Now the second part is it the surface or is it the interior points? If we look at our actual surface, we know that if I were to look at these points right here, these points all have a norm of exactly 1. So it's definitely going to contain the surface. But if we look at, let's say, a point in here, this point would have a norm of less than 1. And if we look at our restriction, less than 1 is still actually possible. As long as my norm is less than or equal to 1, it's considered valid. So we know that this would actually be the surface and the interior points. Okay, there's the key. If the question had just that my norm has to be equal to 1, so not less than or equal to 1, but just equal to 1, this would have been just the surface. So I'm hoping that sits well with everybody. They understand what's going on. Great question. What would A look like if it was a cube? My restriction would be something like this, where I would say -1 is greater or equal to x1, which is greater or equal to 1, and then the same thing for x2. So x2, 1, and then my restriction, this would be my restriction. So basically I would have a vector that in 2 dimensions, if I were to actually draw it, and I'll switch over to pink. Oops, just like this. If this was the case, it'd be a cube, because if I were to look in the vertical direction, I'm basically good as long as I'm between 0 and 1. So as long as I'm in this area. And in the horizontal direction, it's the same thing. So as long as I'm between -1 and 1. So if I were to look at this point over here, which is 1, 1, well, that is still within my restriction, so it's good. If I were to look at this point, which is 1, -1, well, this is actually still good. And if I were to just draw all my points, we would see that we would actually end up with a cube. So does that make sense? I'm hoping so, at least. All right, if it doesn't make sense, feel free to stop me. Yeah, it does. Perfect. Wonderful. So let's move on. A little hint for everybody. That's a great question. So that would be the surface and the interior points. Exactly. So what you want to look at is it greater or equal to, or is it just equal to? If it's, or less than or equal to. Since I have the less than or equal to, it'd be all the points and the surface. What I could do though, is I could replace this with just this. If this was the case, it would not be the surface, because I now don't include factors like 1, 1. So this right here would just be the interior points. Yes and no. So if I wanted to, I could leave it so I don't restrict x3. But what would happen is my cube would be infinitely long in that direction. So you still technically get a cube, it would just be infinitely long, if that makes sense. But if I ever were to give a cube, I would make sure that all directions have a restriction present. Sound good? All right, I'm hoping so. All right, the next question is a big fun one. This is one that we did in class today, and we said when it comes to these type of questions, basically the way you want to think about it is in terms of I have an input and I have an output. And how do I go from that input over to that output? So the first one right here is our input, and then the second one over here would be our output. So basically R3 is a 3-dimensional vector. So this is going to be something like X, Y, and Z. And I'm taking this as an input, I'm putting it through my linear map or my function or whatever you want, your computer code, and I want 2 outputs. Let's say that they are just A and B. And what the question's basically asking is this map here that I transformed this vector to this vector, how many constants is it going to need? And if we look here, it's actually not too hard to calculate, because we have to know that if I want to calculate parameter A, it's going to be a function of all of my inputs, right? If I want to calculate an output, it has to be a function of my inputs. So if I were to write this in its most simplistic form, we know that A is going to be some constant times X plus some constant times Y plus some constant times Z. It has to be a function of all of the inputs. Now, some of the constants might be equal to 0 if it is independent of the inputs, but in its most general sense, it's going to be a function of all the inputs. And the same thing for B. B is going to be some factor times X plus some factor times Y plus some factor times Z. And all we're basically doing is saying, okay, I've now defined both of my outputs in terms of my inputs, but how many constants did I need? So if I look, I needed 1, 2, 3, 4, 5, 6. So in this actual question, I'll switch back to red, we need 6 constants. Now, there is a trick to this though. I only showed this here, so I'm hoping everybody can see kind of what the basis is behind it. But all you need to do for these type of questions is find out how many inputs you have, and you multiply it by how many outputs you have. So in this case, I have 3 inputs and I have 2 outputs. So 3 times 2 is equal to 6. And that's all you have to do for these kind of questions. Again, I wanted to show you how this came about, but in general, if this was an exam, this is actually your most simplistic question, because all you're doing is multiplying 2 numbers together. And even though it sounds like it might be a little bit different if we were to move on to question 6, and now we have a matrix, it's actually still the exact same thing. If I look here, I have a 3 by 3 matrix, M3, so we know it's going to be something crazy like A, B, C, D, E, F, H, I, J, or I forgot G, but it really doesn't matter. I know I can't do the alphabet, but I'm taking a 3 by 3 matrix and I'm transforming it to R. So R, we all know, is just a single number, which we will call, let's say, Z, just like this. And the same principles apply. I'm going to take the number of inputs that I have here and multiply it by the number of outputs. So in this case, I have 9 inputs and I only have a single output. So in this case, I'm going to need 9 constants to define this transformation. So how does this question sit with everybody now that you know the trick? Is it easy once everybody knows the trick, or is it still pretty challenging? Easy? Perfect. This is another great question to know for the midterm. Wink, wink. I have it turned on my camera, but my basement's a mess. I'm still moving in, so nobody gets to see the filth that I live in. All right, on to the next question. It says, consider the following symmetric matrix. If the eigenvalues of S are lambda 1, lambda 2, and lambda 3, then the following is true. One thing I always recommend in these exams is always make sure if it's asking if something is true or false. In my exams, I don't have a lot of them. I think it's very few, but you'll notice in these older midterms, the old professor loved to have these true or false type questions, and it can become confusing. The only thing that you want to make sure you do when you do these exams is make sure you read the question very carefully. So in this case, we want to know what is true. Now, here's the trick for you. If you ever see these two words together, symmetric matrix, as well as the word eigenvalues, basically this is going to be an invariant question, because my invariance of S, so I1 of S, this has to be equal to the same invariance of my diagonal matrix S prime. And the same thing for I3 of S has to be equal to invariant 3 of S prime. Where S prime is the diagonal matrix, and even though it's not written in the question, it's written as one of the answers, this would be S prime right here. This is the big property of these diagonal matrices. So all you want to do in these types of questions is just compare the invariants. If we look at part A here, I'm going to erase the highlighting. It has lambda 1 plus lambda 2 plus lambda 3. If we look here at our diagonal matrix, they're adding this diagonal column. We know that that is the trace of a matrix. So we know that the trace of S prime, which is equal to the first invariant of S prime, so invariant 1, this has to be equal to the trace of S. So if we were to look at S, we can calculate the trace because we know it. It's going to be 2 plus 0 plus negative 2. If I add all of that up, I get that it's equal to 0. So if I were to look at this question, It's saying lambda 1 plus lambda 2 plus lambda 3 is equal to 0. This is absolutely correct. So there's the first one. We know that the trace of s prime has to be equal to the trace of s, and we calculated the trace of s as 0. Now, this is why you always have to be careful, because most students will say, okay, this is true, they circle it, they move on. However, we should always look at the other options to see if there's something else. The second part right here says that lambda 1, lambda 2, and lambda 3 are all real numbers. Basically, there's no imaginary numbers. And if you just go look at our notes for symmetric matrices, you will see that this is also true. If we ever have a symmetric matrice, so I'm just going to put symmetric right here. If we ever have a symmetric matrice, it will always have real eigenvalues. The third one says there's a coordinate system in which S has the form of S prime, which is the diagonal matrix of the eigenvalues. This is absolutely correct. So for 7 here, the actual answer would be all of the above. Okay? So remember, if you ever see symmetric matrice and eigenvalues together, it's usually going to come into these invariant type questions, where we can relate the invariance of S here with our eigenvalues. So lots of fun. Hopefully not too bad so far for everybody. Again, if I'm going too fast or you need clarification, just let me know. We're going to move on to the next one. It says, let A and B be three-dimensional, non-zero vectors, and it says then the orthogonal projection of B onto A is equal to, and this is probably the easiest question you will ever get, because if we were to go to our formula, the projection, and this is B onto A, so it's going to look like this. This is going to be equal to B dot A divided by the norm of A squared multiplied by A. And if we look at our answers here, well, it's actually just answer B. So if you were to look at the class notes and then have this question, it's that simple. What could have happened that may have tricked some students if they were to rearrange this? So let's say that they wanted A on B. What may have tricked some students is this actually doesn't appear anywhere, because if I were to do my projection of, I guess, A onto B, we know it's going to be A dot B divided by the norm of B squared multiplied by B. And if we look here, there's no actual answer for that. But always remember that the norm of a vector squared is equal to the vector dotted with itself. Okay, so always remember that. Because if this was the question right here, A onto B, and I were to do this formula is actually the exact same as this formula right here. Okay, so this is the only trick that someone could throw at you in these type of questions. But again, this one actually had no trick. All we needed to do was just look at our notes and say, okay, I know the formula, I'm good to go. Just circle the answer. Another great question from Jamal in the chat. Does the dot product of A and B equal to the dot product of B and A? Yes. So the rule of thumb is this. A dot B is equal to B dot A, but A cross B does not equal to B cross A. So those are the only big properties that you should always remember. I hope that answers your question. Remember that the dot product is just taking components and multiplying them together. So if I have 1 and 2, it doesn't matter if I go 1 times 2 or 2 times 1. They're going to be the exact same in the very end. All right. So I think I answered your question. If not, just throw another question out in chat. We'll move on to the next one. All right. It says let U equal to n, 1, and 3, and v equals 0, 1, and 0. Then the orthogonal projection of u onto v is the vector. And basically, it's just a projection question. But this is when properties become very, very handy to know. Is this right here an axis? Is this an axis that we all know? Yes, exactly, Jamal. This is our E2 axis. And if we would look at U, it already gives us the component in that direction. The component is equal to 1. So we know that if I want a vector, let's just call it vector A, it's going to be the magnitude of something, so we'll say A, multiplied by the direction of A. Well, we know that the magnitude is equal to 1, and we know that it's going along the E2 axis, which is 0, 1, and 0. So we know that this is automatically going to be 0, 1, and 0. It's one of those very nice questions. So I already know that this is going to be B. However, let's say that you don't know any of this. How else can we solve it? Well, we already know the projection formula. So what I could have done is I could have said, okay, I'm finding the projection of U onto V. So V is going to be at the bottom, U is going to be at the top. And we know it's going to be U dot with V divided by the norm of V squared multiplied by V. Now, if we were to consider V, we already see that V is a unit vector. So we know that the norm of V is equal to 1. It's already a unit vector. So basically, my projection, I'll do it right here, becomes U dot V, which is going to be a scalar, multiplied by my vector V. So if I were to do my dot product really quick, so this little part right here, I'm going to have 10 multiplied by 0 plus 1 multiplied by 1 plus 3 multiplied by 0. If I were to do the calculations, I get this is equal to 1. So we know that this formula right here is simply going to be equal to V, and we already know that V is, oops, not 1, 0, 1, and 0. So I'm hoping that makes sense. There's a trick to do it quicker, but if you do it the long way, I'm using quotation marks because as we see it, it's not that long, but you can figure it out either way because we already know the formula for an orthogonal projection. So hopefully not too bad thus far. I got a direct message saying, can you explain the trick again? Of course, I'd be happy to. Again, what we're doing when we deal with the projection is we're basically asked to find the component of this vector along a direction. And if we look at this particular question, it says find the component of U in this direction, but this direction is the y-axis. So what this question really asked me is, what is the component of U along the y-axis? Well, we know from basic vectors that the component is going to be that middle one. We know it's already going to be 1. We already know it's going to be along the y-axis. But what this wants is the actual vector itself. And vectors are going to be a magnitude times a direction. We know that the magnitude is going to be this one right here. And we know that the direction is going to be this right here. So I just take 1, I multiply it into V, I get the exact same thing, and that's how I found out the answer to the question. So I hope that answers your question about the trick. Again, you don't have to worry about it too much because the long way is pretty quick as well. Alrighty, so just actually one more note on this. You all have access to Mathematica, MATLAB, whatever you want. It'd be pretty easy to before the exam, program a projection. So all you have to do is enter in the 2 vectors, right? So yeah, it shouldn't scare students too much. All right, so number 10. This is another great question to know for your midterm. It says that if Q1 and Q2 are reflection matrices and Q3 is a rotation matrix, then which of the following is false? Now, whenever you see a question like this, where they give you a bunch of matrices, and they say they're either reflection or rotation, what we need to take note of is the determinants. So if I have a reflection matrix, we know that the determinant is equal to -1. So if I know that Q1 and Q2 are reflection matrices, then I know the determinant of both of them has to be equal to -1 because they're reflection matrices. Similarly, since I know that Q3 is a rotation matrix, I know that the determinant of that one, Q3, has to be equal to +1. So that's the first thing that you always have to remember for these questions. And what will typically happen is they will always ask this right here. What is the determinant of all three matrices multiplied together? And the trick is that the determinant of all of them multiplied together is just going to be the determinant of each one multiplied separately. This is one of the very nice properties of square matrices. So Q2 plus the determinant of Q3, we know what each one of these is, so we know that this is going to be the determinant of Q1, which is -1, multiplied by the determinants of Q2, which is -1, multiplied by the determinants of Q3, which is 1. We get that my determinant for all three multiplied together is equal to 1, plus or +1. That's the key right here. So if we look here, is my determinant equal to 1? Yes. We can do the calculations. We saw that it's equal to 1. Since our determinant is not equal to 0, is the matrix invertible? Absolutely. Remember, for a matrix to be not invertible, the determinant has to equal 0. Since our determinant is not equal to 0, it is invertible. Now, our last two questions are basically what we already talked about above. Is this a rotation matrix, or is this a reflection matrix? Well, since we have a determinant of +1, we know it's going to be a rotation matrix. If I had a reflection matrix, it would have a determinant of -1. So in this case, we know that for 10, answer D is going to be the false one. Does that make sense to everybody? I'm hoping so. As we can see, these questions hopefully aren't too bad for everybody. Now, there are going to be some questions in the midterm that scare some students, which make them think that the midterm is going to be hard. Question number 11 is one of those questions, but don't worry, I wouldn't test a question this bad on the midterm. I think that question 11, if you were to have done this beforehand, probably gave a lot of students some trouble. But you don't have to worry about question 11 because it's kind of mean. Now, you actually have everything to solve it. You just don't know because I haven't talked about it in class. Basically, it's this. We have a matrix M that is invertible, and we have a second matrix N which is not invertible. Then it says, what is true about the matrix NM? So basically, I take an invertible matrix and I multiply it by a not invertible matrix. So if we were to look here, if my matrix is invertible, so in this case that is M, we know my determinant cannot equal 0. On the other hand, if I were to look at N, which is not invertible, we know that this one has to equal 0. And just like we did above, if I want the determinants of the matrix multiplied by each other, so in this case N times M, it's going to be the two determinants multiplied by each other. So this is going to be equal to something that is 0 multiplied by something that is not equal to 0. But at the end of the day, we know it's going to be 0. 0 times anything is going to be 0. So what this tells us right here, oh, I don't want to scroll too fast or else I'm going to get the Zoom chat out of the way. What this basically means is that the matrix NM is not invertible because its determinant is equal to 0. So that's the big trick here. Because if we go through, we can actually start to cross some things out. Because what the question wants is it wants a true statement right here. If I were to look at C, it says NM is invertible. Well, we already know that that is false. The other one in part D says that the rows of NM are linearly independent. That is also false. We know for a non-invertible matrix, they are linearly dependent. So that leaves us with two options. Now, option A is something we haven't talked about in class, which is why I wouldn't test a question like this. But option A is actually also false too. A little trick, and again, this is outside of the class, so don't worry about this too much. If A was true, the only possible solution is if my N matrix or my M matrix is some scalar multiplied by the identity matrix. We call it a commutative matrix, but again, we didn't talk about it, so I would never expect anyone to know that. So you don't have to worry about that. The other thing too, it says in the question it must be true. So if you were to have a question like this, but again, I would never test you on something I haven't shown you. But if you wanted to, you can just create two matrices in Mathematica, multiply them together, and you will see that A is rarely true. It has to have very specific conditions. So we already know that it's going to be answer B, but the question is, why is it B? Now, we actually know what B means. It just looks a little crazy because of the wording. Basically, what it says is there exists a vector x such that my new matrix, n times m, I'll write it in matrix so everybody can see it. So we know that this is going to be a matrix that when I multiply it by x, I get 0. And it also says that x, right here, it cannot equal 0. So when I take a matrix and I multiply it by a non-zero vector, I get 0. Does anybody remember what exactly this is? When I have a vector that's non-zero and it maps it to the 0 vector. Exactly. This right here is the kernel. So what B is saying, that this matrix NM, it has a kernel. And since it is non-invertible right here, we know that, yes, this has a kernel. So B is the thing that has to be true. Again, it's a more complicated question because I've never actually talked about this in class, but I would never show you something that I've never talked about. So you don't have to worry about that too much. Again, if you have any questions, feel free to stop me. I'm always happy to answer any questions you may have. All right, looking at number 12, it says let Q be a three-dimensional matrix, or specifically an orthogonal matrix, such that it has the following rows. So the first row is D, the second row is E, and the third row is F. It says, which of the following is a correct statement? So which of the following is true regarding these three vectors? Now, the key here, and it's highlighted, is orthogonal. Now, what this means is two things. The first one is that my determinant of Q has to be equal to plus or minus 1. That's the first one. An orthogonal matrix is either a rotation or a reflection matrix. The second property is that all of the rows and columns have to be orthogonal to each other. Basically, they have to be 90 degrees. Now, if I were to look at the rows, and because of dot product, we know that this means that my first row times my second row, or dotted with my second row, should be equal to my second row dotted with my third row, which should also be equal to my first row dotted with my third row, and this should be equal to 0. This is the dot product. What this does is it guarantees that all of my axes are 90 degrees from each other. So if we know those two properties, then we can actually find out what's going on. The first one says that all my rows dotted with each other should be plus or minus 1. Well, we know that this is actually incorrect. It should be equal to 0. So there's the first property. The second part gets a little bit tricky because it doesn't talk about the determinant. But one thing that we always have to remember that the determinant of a matrix, so I'll say the determinant of Q, we can actually express this as the triple scalar product. So it'd be D dotted with E cross F. Now, one of the nice things about this is as long as we keep the order, we can actually move things around. So as we can see, I can go E dotted with F cross D. So in this case, we know that this right here, this particular part, this is actually saying the determinant. And we know that our determinant has to be equal to plus or minus 1. And if we look here, that is going to be answer number B, because we know our determinant is not 0. If we look at statement D, both A and B are correct. Well, we already know that statement A is wrong, so this, of course, would also be wrong. So I'm hoping that makes sense to everybody. Quick water break. I gotta pace myself. After I do this, I have an Eng 130 lab from 8 to 10 at night, so things are just getting started. I got the 8 a.m. and the 8 p.m. today, so it's a lot of fun. All right. So question number 13 gives us two 5-dimensional vectors, and it asks for basically what is the dot product between these two vectors. The first question, which I'll ask everybody here, is my dot product defined for 5 dimensions? Does anybody remember? Oh, sorry, and I got a direct message. I'm going to go back really quick. So while you think about that, I'm going to go back to a direct message. So the question is why is it, and I'll do this in pink so I don't get it mixed up with the rest. Why is it what we have here and not D cross F? So why is it not this? It has to do with what we talked about permutations, where if I have to do something cyclically. So if I'm going D, E, and F, when we talked about this at the very beginning, I always have to maintain this particular order. So if I start with D, then it has to go E and then F. If I start with E, then it has to go F and then it has to go D. And the reason why it has to do that has to do with the actual cross product itself. Because remember, the cross product is a vector that's perpendicular to a plane. So it can either be going up or it can be going down. To ensure it maintains the right direction, we always have to go with this right here. But don't worry, I would never explicitly test that, because that is something outside of the scope. I'm just showing you this to show you why it is the way that it is, but you don't have to remember this permutation. It's outside of the scope of this course. So hopefully that helped explain that. So I'm just going to erase it, and we're going to continue on. Yeah, no problem at all. All right, so my question was, is my dot product defined for 5 dimensions? What does everybody think? No? Okay, so we got a no in the chat. Any other takers? Kevin? I know you're in there, Kevin. Yes? Okay, so I got a yes. Now some controversy. Kevin doesn't know. So Kevin, you're the same as in a lecture. It's funny because I think Kevin actually knows the most. Kevin knows more than me, but he's just being modest. So here's the fun part. The cross product, or sorry, the dot product is defined for any dimension vector space. Any dimension. So this answer right at the bottom where it's not defined is automatically false. It's always defined. The one you have to be careful of is the cross product. So the dot products, so I'll go just dot. This is defined for basically any dimension vector space, Rn. The cross product, on the other hand, is only available in 2. It's available in R3 as well as R7, and that's it. So that's one of the tricks. However, it's valid for 5 dimensions, and in order to actually do it, all we have to do is dot it the same way we would a 3-dimensional vector. So we're just going to take all the components and multiply them by each other. So we're going to have 1 times 0 plus 1 times 0 plus 1 times 0 plus 1 times 0. And then at the very end, it's plus 1 times 1. So we know that our dot product is actually equal to just 1. So our answer is going to be A right there. Hopefully not too bad. All right, 14, I assume is going to cause students a lot of trouble. This is something that I wouldn't test directly because it's kind of a mean one. It's something that everybody has the capability to solve, but it would take a long time. So it says, consider the following symmetric matrix. If the eigenvalues are 0, 1, and 0, then the following is going to be an eigenvector of S. So we know that for eigenvectors, we're basically solving the following, where we're going to take S, we're going to multiply it by an eigenvector, and we know that this is going to be equal to my eigenvalue times the eigenvector. So the one way everybody could solve it is just through trial and error. You could try this, see if it gives you one of the combinations. If not, then you can try this, see if it gives you one of the combinations. Very brutal method. It would take a long time because you have to check this vector for 3 different eigenvalues, and then you have to check this vector for 3 different eigenvalues, and so it takes a long time. There's a lot of combinations to consider. Yes, EV is my eigenvector. I'll write that down real quick. EV is eigenvector. Now, the trick to this question, which is something we didn't talk about this year because we don't really need it. Again, I'm trying to slowly cut out the stuff we don't need. But the trick to this question, if you wanted to solve it, is if you ever have a repeating row, as we can see right here, those 2 rows are the exact same. That row is an eigenvector. So we know that one of the eigenvectors, based on the repeating row, is going to be equal to 0, 1, and not 0, 0, 1, 1. So that's the trick to this question. But again, I'm not testing this question, so you don't have to worry about it. The one thing that I want everybody to remember is that eigenvectors can have any form as long as they are just a scalar multiplication. So I can have my eigenvector as 0, 1, 1, or I can have my eigenvector as 0, 2, 2. They're the exact same. All an eigenvector does is basically create a line. So I'm going to create a line right here. And this line can be defined by many different vectors. So let's say I have my point here. I can define it using, let's say, this vector right here. If I want to, I got to pick a different, brighter color. I can define it using this extremely long vector like this. Or if I wanted, I can go back in this direction and define it using a vector like this. This is why there is an infinite amount of eigenvectors. But if we look, they're all just a scalar multiple of each other. But if we were to compare the eigenvalue that we got, we can see that it's actually going to be answer A. Again, this particular question won't be tested, so don't worry too much about this question. All right, so this is also a fun one. If we look at 15, it says let I be the identity matrix in 3 dimensions, and let P be a positive scalar. Now consider the tensor A, or the matrix A, which is equal to P times I. Which of the following is false? Now if we look here, we know that A is just going to be P times I, and if we want to, we can actually write that out very nicely. It's just going to be P 0, 0, or poo, 0, P 0, or 0, 0, P. And then we can just look at the different things. So if we look at the first one, it says that the first invariant of A is equal to 3P. Well, we know that our first invariant of A is equal to the trace of A, which is the sum of the diagonal terms. So if I were to add them up, we know that this is going to be P plus P plus P, which is just equal to 3P. So we know that this right here is absolutely correct. If we look at the second answer, part B, it says that A is a three-dimensional matrix. Well, we can see since we wrote it out that this is absolutely correct. If we look at C, it says that A is just a single number. We already know that that's incorrect. A is a matrix, not a single number. So we know that this right here would be false. If we look inside of A, so I'll switch to a different highlighter. Actually, red on red would be pretty bad. The elements inside of A, such as 0, they are single real numbers, but we're considering A as a whole. This is A as a whole. And as we can see, this is not just a single number, it's actually a 3x3 tensor, or a 3x3 matrix. So we know that that is false. If we were to look at C, we can easily see that this is true because we can visually see that it is indeed symmetric. So hopefully not too bad of a question. We're going to move on to the next one. It says consider the following symmetric matrix, and it says if the eigenvalues of S are 3, 2, and 1, then the third invariant of S is equal to something. Again, if you ever see the combination, and I'm just going to switch my highlighter, of symmetric with eigenvalues, you always want to think of determinants. Now, we know that the third invariant, so I3 of S, is equal to my determinant of S. We also know that because of a symmetric matrix, this has to be the same as the third invariant of S prime. And we know that S prime has the following form, where it's just going to be a diagonal matrix full of the three eigenvalues. So we know it's going to be something like 3, 0, 0, 0, 2, 0, and 0, 0, 1. Now, if we wanted to, in Mathematica, you can find the determinant of this, but it would take a lot of time. That's the exact reason why there's so many decimal places. I think that the prof said, you know what, if you want to do it in Mathematica, be my guest, but I'm going to make you waste a lot of time. If we were to consider S prime, we know that the determinant of S prime is just going to be the three eigenvectors multiplied by each other. So my determinant of S prime is just going to be equal to 3 times 2 times 1. If we do that, we get that it's equal to 6. So we know it's going to be answer C. So that's the nice thing. Again, if you ever see symmetric with eigenvalues, you're basically going to look at the invariants. That's all we're doing. The determinant is the third invariant, so it was actually kind of nice that the question said third invariant. If they wanted to be a bit more mean, they would say the determinant of S is equal to something, and then intuitively you would have to figure out on your own that we can use invariants to make this question rather simple. All right, so moving on to the next question. This again will be a question that's not tested because I didn't talk about it. I think it's really unfair to test questions that I don't talk about. I'm not that kind of guy, so if you're sad about that, I apologize. I'm sorry, but I'm not going to test questions that I didn't teach you guys. I don't think that that's fair. So if we were to look at this question, we basically have three vectors, u, v, and w. And the way that they are right now, we know that they can actually form a parallelogram, or a parallel piped, whatever it's called. And basically a cube with some angles. And what we're going to do is we're going to transform these three vectors by a matrix M. So I take this matrix M and I now get 3 new vectors. And these 3 new vectors create a different parallel piped or whatever it's called. Now, one thing that I told everybody is that if I want the volume of one of those parallel piped, basically it's going to be the triple scalar product. So it's going to be U dotted with, what are the other two called? V cross W. So this would be the original volume. So I'll put this as V naught. And then our new volume is going to be MU dotted with MV cross MW. So if you want to solve this question, you definitely can. But the reason why I don't test it is because doing it this way is not really the trick. This question has a trick. If you were to do it this way, it would take forever. The trick is that if I want to compare the volumes to my original volume, so V divided by V naught, this is actually always going to be just the determinant of my transformation, M. And if we look at M up here, and we were to do the determinant, it's a rather simple matrix, we would find that it's equal to 1. So we know that the answer would just be B. Again, I didn't really show the trick previously, so I don't think it's fair to test it, but you have seen this before. Remember now when we talked about strain, how if we wanted to see if something is expanding or contracting, we would take the determinant of our deformation gradient F. That's why, is because what that does is it gives us a measure of volume before and after the deformation. So we've seen this before in kind of the second half of the course, but since I didn't talk about it in the first half, I'm not going to test it. Again, if you're disappointed with that, I'm really sorry, but I want to try and be as fair as possible. All right, so now we're going to move on to the next one. Now, the next one is an incredibly simple question, but I think it confuses a lot of students. It says, let M be a 3-dimensional matrix and X and Y be 3-dimensional vectors. It says, if Mx is equal to this and My is equal to this, what is Z? The thing to remember is if we look at the definition of a linear map, so this is way back at the very beginning, if we look at the definition, it says that M times Z should be equal to, and again this is the exact definition, M, and if we substitute Z, it's 2x minus 5y. This should be equal to the same as if I were to apply the map separately. So this should be equal to 2 multiplied by mx minus 5 times my. Again, the reason why I do this is the definition of a linear map. Now, if I were to look at my very end here, I take 2 times mx minus 5 times my. I actually know all of those variables. So we know that mz is going to be equal to 2 multiplied by x, which is 1, 1, 1. Oops, my brackets are getting a little crazy here. Oop, there we go. It's trying to get away from me, but I didn't let it. Minus 5 times my. And if we look at my, it's 1, 0, and 1. So if I were to just do this very simply, we know that we are going to get the vector 2 minus 5, which is negative 3. We have 2 minus 0, which is 2, and 2 minus 5, which is negative 3. So it's going to be this, and if we look at our options, this is option B. So again, it looks like it's a very weird question, but we can actually figure it out. The trick here is that we were given enough information to calculate mz. But if I asked for z by itself, then you would actually not be given enough information. That's the trick here. If I asked for just z, we would not have enough information. But since I asked for mz, or they asked for mz, we're good to go. All right. moving on, this is a great question. I promise you, I don't think this is on the midterm, but it's still a really fun question. If we look here, it says, which of the following is a Euclidean vector space? So the key here is Euclidean. Now, a Euclidean vector space has three things. One, it has a norm function. Two, it has a distance function. And then three, it has basically a dot product, or a function to define geometric angles, or the geometry of two vectors. If we were to look at option number A here, it says that it's a finite dimensional vector space where it has a norm function, a metric function, and an inner product function defined. The problem with this one is it says inner product function. The inner product function is a very general term. Now, the dot product is one example of an inner product function, but it's not exclusive. So this would actually be incorrect. The reason why is because for a Euclidean vector space, we need the Euclidean dot product. We can't just have a very random inner product. We have to actually use the Euclidean dot product. Answer B says a finite dimensional vector space where it has a norm, a metric, and a distance function not defined. So in this case, it says that these functions are not defined. We know that that's absolutely incorrect because they have to be defined. If we look at C, it says it's a vector space with norm, metric, and distance function, or sorry, norm, distance, and dot product function, but it actually defines what these three are. And if we look at these three functions, these are the ones that we talked about in class. So we know that this would exactly be true. So this is the true one right here. D we know is false. It can't just be any dimensional vector space. It has to be one with very specific functions defined. Just out of curiosity though, because I want to know, does anybody know an example of an inner product function that's not the dot product? No? Yeah, I don't blame you. I learned about my first one last year. It was an eye-opener how gross and disgusting everything is. Basically, what we can do is we can start taking this inner product function, and we can essentially, and I use this very, very lightly, we can take the dot product of matrices. We can take the dot product of tensors. It's not exclusive to just vectors. But that's way beyond the scope of this course, so you would never, ever see it. All right, we're going to go to the next one. And this is a great question. This is a question to remember, especially for the exam coming up on Thursday. It says, let M be a three-dimensional matrix, and it's basically the identity matrix. If we look right here, this right here is equal to the identity matrix. Now it says the following is an eigenvector of M. And this is something that if you rely just on Mathematica, you're going to get the answer wrong. If you follow Mathematica, everybody here is going to say it is equal to A. But it's not. A is true, but the actual answer is all of the above. So this is something to pay attention to. Any non-zero vector is an eigenvector of our identity matrix. Any non-zero vector is an eigenvector of our identity matrix. That means that this is an eigenvector, this is an eigenvector, this is an eigenvector. It looks like it's some pretty crazy stuff, but it can be very easily proven if we remember what exactly an eigenvector is. It's basically our matrix multiplied by an eigenvector. In this case, we'll define it as x, is equal to lambda, or eigenvalue, multiplied by x. Now, for the identity matrix, and you can find this out in Mathematica, lambda is always equal to 1. So basically, we have our identity matrix multiplied by an eigenvector is equal to that eigenvector. Now, if we look at the identity matrix, and I'll ask everybody here in the chat, if I multiply a vector by the identity matrix, is it ever going to change? What do you think? Okay, yeah, so Madeline got it. No, it's never going to change. If I take even a tensor and multiply it by the identity tensor, nothing changes. So if this right here never actually influences anything, I can just get rid of it, basically, because it doesn't do anything. So we basically get that any eigenvector will satisfy this condition. So that's what's a very specific property of the identity matrix. Any non-zero vector is an eigenvector of I, which is very beautiful, right? So it's pretty crazy. If you don't know that, chances are you're going to get it wrong, because Mathematica only provides, I believe, 3 eigenvectors. It doesn't actually show that there's basically an infinite amount of eigenvectors. All right. Moving on to the next question. It says, let M be a 2 by 2 matrix where M is 1, 0, 1, 0. Then the kernel of M is equal to whatever. Now, if we remember the kernel of M, basically we're taking M, we're multiplying it by a vector, and this should give us the 0 vector. That's all we're doing for the kernel. I'm just going to erase this really quick so it kind of stays out of the way. Now, if we consider what exactly we have, basically we're looking at this scenario right here, where we have 1, 0, 1, 0. That's M, which we were given. We're trying to find a vector, which we will call x1, x2, and this has to be equal to 0, 0. Oop, I did one too many squiggles on that one. I was going a little crazy there. Now, if I were to write this in equation form, we have 1 times x1 plus 0 times x2 is equal to 0. And then for our next one, we have 1 times x1 plus 0 times x2 is equal to 0. Now, it's very easy to tell that x2 right here can be absolutely anything we want, because since x2 is always multiplied by 0, it doesn't matter what x2 is. If it's 1, who cares? It's multiplied by 0. If it's 69, who cares? It's multiplied by 0. So we know that the kernel here is going to be option A, where x2 can be absolutely anything and x1 has to be equal to 0. So hopefully that makes sense to everybody. If we were to look back at our other options right here, the kernel of M is the 0. Well, that doesn't make any sense. Remember that the kernel should always be a non-zero vector that maps to the 0 vector. None of the above, we already know that's not true. Option C says that x1 can be anything. Well, we know that that's not true, because if I were to take one of these equations, let's say this one right here, and I were to have x1 is even equal to 1, well, we get 1 is equal to 0 in our equation. That doesn't hold true at all. So we know it's not going to be option C. So hopefully that makes sense to everybody. All right, another fun little tricky question. If we were to look at 22, it says let M be a 3-dimensional matrix, and it gives us the 3-dimensional matrix. And it says, which of the following is an eigenvalue of m? Again, this is another classic trick question. If you know the trick, this takes 2 seconds. If you don't know the trick, then this is going to be basically a plug and chug in Mathematica. So it's still not going to take a long time, but if you know the trick, this will take all of 2 seconds. The trick here is realizing that this row right here is all zeros. This indicates that this is linearly dependent, or in other words, this is not invertible. Now, if something is not invertible, then it's guaranteed that one of the eigenvalues has to be 0. And this can be proven pretty simply. Remember what exactly an eigenvalue is. If we go m times, I guess, an eigenvector is equal to lambda times that vector. If something is not invertible, it has a kernel, which basically means that m times lambda, or I guess, no, sorry, our eigenvector is equal to 0. If we were to compare these two cases, the kernel and the eigenvalue, they're the exact same thing, but for lambda equals 0. So it's actually one of those fun things. The kernel, if you were to look at it from a very general perspective, it's actually the eigenvector associated with lambda equals 0. That's all it really is. So again, if I were to know the trick, I can just immediately circle, hey, it's going to be equal to 0. If I don't know the trick, it's no problem. I throw it into Mathematica. Mathematica will give me the 3 eigenvalues. You're good to go either way. Again, it's just about saving time. All right, so hopefully everybody is still doing well. We're almost at the end, everybody, so hang in there a little bit. Last questions are pretty simple. Okay, there we go. It says, let M and Q be 3-dimensional matrices, and let N equal to QM times Q transpose. Now it says, assume Q is a coordinate transformation matrix. Then the following has to be true. So if we look here, we're basically taking a matrix M and we are rotating it. So that's what we're doing. If we look at what we're doing right here, we are just doing rotation or reflection, but I want you all to think of this as simply just rotating. That's all we're doing. Now, we said that when we rotate something, there are certain things that remain invariant. That's the key. We have certain things that remain invariant. The first one is the trace. The second one is something gross that you rarely need to know. And then the third one is my determinant. If I were to go through a lot of these answers, it basically solves a lot. So which of the following has to be true? Well, the first one that's true is the trace should be equal to the trace. That one's true. It's invariant. The third one is my determinant should be equal to the determinant. Also true, because the determinant is also invariant. So right away we know it's going to be D, which is all of the above. But the last one is the eigenvalues of M are the same as those of N. Now, I don't think we talked about this directly, but yes, the eigenvalues are also invariant. They never actually change. This kind of goes into the second invariant, but it's not very clear, so I kind of left it out. But basically what I do to show this one is I just take an actual stress cube that we've been talking about lately, and we know that in a general state it's going to have normal stresses in every direction, and it's also going to have some shear stresses. So something like this. And we said that we can actually rotate this cube. Oops, that didn't work out well at all. All right, let's go round 2 and see if it's a little bit better. Okay, that's not too bad. Wait, no, I wanted it rotated. Oh, that would have worked. All right, here we go. Perfect. We can rotate this cube, so the only thing that we have are our principal stresses. Now, let's say that this requires rotation of 50 degrees. If I were to have rotated my cube something less than 50 degrees, let's say I only rotated it, actually I think I'm starting to get out of the drawing picture. I'll go down here. If I were to only have rotated it, oh, this is not going to work for me, is it? Come on, please, please, please. Thank you. If I were to only have rotated it 20 degrees, so theta is 20 degrees, I would still have some of my shear left, because my shear hasn't completely gone away yet. My shear would be less, but it is still technically there. The key thing that I'm trying to say is, even though I rotated my cube a little bit, my principal stresses are never actually going to change. I'm slowly getting to them, but they're never actually going to change. The only time principal stresses start to change is when I actually deform something or transform something through deformation. So the principal or the eigenvalues or the principal stresses, principal strains, they never change when you rotate something. That they're actually invariant. So this would be all of the above. All right, going on to the second last question. This is a very nice question. You probably will have something like this on your midterm. Another hint, if you will. And it says, which of the following one of these maps is surjective? Now, we have to keep in mind that when we're looking at these maps, we basically have two things we look for. Injective, which means that every output only has one input, or surjective, which basically means that every output has an input. Not one input, but it's just accounted for. So I'm going to scroll down a little bit. Basically, I want to write that what we're looking for is that every output has an input. If we're just looking for surjectiveness, has an input. So if we look at these maps, we know that this is going to be our inputs. These are going to be our outputs. And we want to just make sure that every output is indeed accounted for. If we were to look at our first one, this one's accounted for, this one's accounted for, this one's accounted for, and this one, we'd actually find that right away that this has to be our answer. But let's look at the rest and see. If I were to look at answer C, we can see that there is an output that doesn't have an input. So this one would not be surjective. If I were to look at answer B, there is a bunch of outputs that do not have an input. So this one is not surjective. And then the same thing for D. There's a couple here that have no inputs, so it would not be surjective. Now, I'm going to answer this because I think it'll get asked almost immediately in the chat anyway, is what happens if it was asking about injectiveness? Well, again, injective means that every output only has one input. So if I were to consider, and I'm going to highlight it, this over here, this would not be injective, because as we can see, these two inputs, this one and this one, they give me the same output. So that's what I would look for if I was testing injectiveness. How many times does two inputs give me the exact same output? You don't want that to happen. Basically, if I want an injective map, part B here would be a great example, because every input only has one output. So I'm hoping that makes sense to everybody. Hoping so anyways. You never really know. All right, the last one, and this one is actually kind of amusing today, because some of the professors were talking about this and they were curious if students knew the significance of these signs. Because usually we think that these signs are pretty self-explanatory, but we get a lot of questions about them, so it's kind of funny. Now, the trick to these questions, if you ever see a question like this, it's not so much the information. What we're really testing is these signs right here. Remember that if I have a double arrow in the case of this first one right here, it means that one statement implies the other and vice versa. So if we look at the question, it says which of the statements is false? Now, the first one says if my determinant of m is greater than 0, it's invertible. That's exactly true. Invertible. However, this is actually the false statement. And the reason why is this. This statement implies that yes, it is invertible. However, if something is invertible, that doesn't always mean my determinant is greater than 0. So this actually does not hold true. And that's why this statement is false. This little arrow right here implies that the statement works either way. Remember that to be invertible, my determinant can, yes, be greater than 0, but my determinant can also be less than 0. And since this side doesn't include that less than 0 part, I can't actually go that direction. I'm hoping this makes sense to everybody. For instance, if I were to look, and this is a good example too, if my determinant of m is equal to 0, we know that it is not invertible. This statement works both ways, because if I were to tell you as students that your determinant is 0, you know it's going to be not invertible. However, if I were to tell you if the matrix is not invertible, you also know, going backwards, that my determinant has to be equal to 0. Again, you can't do that with the first one. If I were to tell students that my determinant is greater than 0, yes, you would know it's invertible. But if I were to tell you that the matrix is invertible, you don't know that the determinant is positive, because the determinant could also be negative. So I'm hoping that makes sense to everybody. Does it, or does it not? Probably put everybody to sleep by now. It does. Awesome. Thank you for answering, Jamal. So this right here is the end of the exam. So real quick, I just want to ask before everybody leaves, did this session help? Do you feel more comfortable now that we went over one of the midterms? For sure? Wonderful. Perfect. That's all I want to know. Even Kevin answered, so tonight's a really, really good night. Awesome. So that is it. After I'm done, I'm going to upload it so that everybody can rewatch it if they want. I posted the PDF solution too. So if you want to just look at that, that is posted. I did a nicer job than what I wrote down here. And if you want more practice, I did the exact same thing for the 2014 midterm as well. Personally, I would say that if you do the 2014 and the 2015, you're more than fine for the exam. The exam is very similar format to this. And as you would see if you do multiple exams, a lot of the questions start repeating because there isn't a lot to test, basically. If I wanted to make it hard, I would have to go over concepts that I didn't teach, and I don't think that's very fair. The test will only include stuff that is for sure in the lecture notes or can be easily derived from the lecture notes. So I hope it's a fair exam. So that is it. I hope you all have a wonderful night, and I will see you on Thursday for the exam. If you have any questions, feel free to email me. I also have office hours basically all day tomorrow. I might leave around maybe 3 or 4 o'clock because I have to teach Eng 130. But from 8 a.m. all the way until 3 o'clock, I'll probably be in the office. All right, so have a wonderful night, everybody. Jamal, I see your message, so I will stick around. But for the rest of you leaving, have a wonderful night.